Welcome to qnawire.
Okay, so a lot of observations and experiments were made on our unknown substance X. First, what we're going to talk about is the fact that it was determined to be 40% carbon, 6.71% hydrogen, and 52.39 oxygen. Okay, the first thing we'll want to do is convert these to relative masses. The way we do that is we just divide by the lowest percent that we have. So we're going to divide everything by 6.71. Okay, so let's see, 40 divided by 6. Get 5.96. And I get 1 for hydrogen. And let's see, 52.59 divided by 6.71. We get 7.8. Okay. Point here is that this is basically telling us the mass ratios of our various components. If we divide each of these by the molecular weight of those components, then we'll have a mole ratio, right? So we divide this by 12, divide this by 1, and we divide this by 16. These are roughly the molecular weights of each of these components. What we'll get is 0.5, 1, and 0.5, roughly. It'll actually be like 0.498 and 0.49. You know. What this is telling us is that we've got, CnHn over 2ON. That's our formula. Okay. Next, we're told that the molecular weight is 90. Okay. All right. So, what does each of these mass units weigh up to? Like, if n equals 1, what does everything weigh? If n equals 1, it's going to be 12 plus 1 plus 16, and that's going to equal what? 29, right? Roughly. Right, so n probably equals 3. The point is, right, it would take 3 of those to take up 90. Roughly. Oh, I see I made a mistake. This is actually supposed to be 2n. There we go. That makes more sense. So given that that's 2n, this should be, if n equals 1, we should have 12 plus 2 plus 18, or plus 16. Right, these are the molecular weight of 1 carbon, molecular weight of 2 hydrogens, molecular weight of 1 oxygen equals 30. So we know n equals 3 because 3 times this 30 is going to give us 90. Basically, what that is saying is that the empirical formula is C1H2O1, and that the molecular formula is C3H6O3. Okay. Let's see, where are we now? Draw possible structures of X that fit the molecular formula and contain one double bond. Okay, so we could have, and then we want to ignore having cyclic structures. Yeah. Yes, and they're just telling us to not make bonds to oxygen to itself. So my guess is that it's likely some sort of maybe something like this. Would this make sense? let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3. That's probably it. I can't say for sure though. Could also be something like this. Okay. Kind of running out of options. I guess we could have something weird like this. Right, there's actually like a ton of options. Yeah, when it says draw the possible structures, I mean, you could go on for quite a long time, I feel like. Um, Basically, as long as there's a single double bond, 3 carbons and 3 oxygens, the hydrogens are going to make themselves the correct number just based on the way that formulas work and double bond equivalencies are calculated. So, I don't know. Here's some options. Let's see what else it knows for us. Has to give us. What is the structural significance of the observed optical activity? Okay, so it does. Okay, so dissolves readily in water to give an acidic solution and demonstrated optical activity when tested in a polarimeter. Okay, so if it demonstrated optical activity when put into a polarimeter, that means it needs to contain a stereocenter. None of what I've drawn so far contains a stereocenter, so we may want to reconsider, right? So what would be something we could do? Let's see. What if instead we have something like this? We need to basically develop a structure that does have stereoactivity, right? So now we've got 2 carbons left. We could make this an OH, right? This would be valid, and this would be a stereocenter, right? Because it would contain a bond to hydrogen there, and it would have 4 different substituents coming off, right? So this is probably our most likely structure so far, based on that information. Okay. The structural significance of the observed optical activity means it must contain a stereocenter, a carbon with 4 unique substituents. Okay. What is the structural significance of the observation that solution X was acidic? Well, we know that it contains an OH. Okay, and here I'm sort of seeing another option, right? So this is like an ester, but we could have also had this carboxylic acid. 1, 2, right? This would also have a stereocenter, and it would have the correct formula. Okay, this would actually be more acidic than this one. So this is a little more likely. Okay, what is the structure of X? Well, it's very likely this. This is very likely the structure of X. Is more than one structure consistent with all the data? Yeah, I'd say that, right, it's not perfect. But this is also, somewhat possible. This is technically an acidic proton, right? It's not as acidic as this proton. It's not on a carboxylic acid. But there's no reason why this couldn't. Yeah. I guess if it readily dissolved in water, it's more likely that it had a very easily removable proton, right? Because it would form an ionic compound as soon as the proton was abstracted. So this is the most likely. This is maybe possible.